The current era of zero-shot image Inpainting is dominated by 10 billion parameter foundational models like Flux.1 and Stable Diffusion 3.5. These models carry massive memory footprints and require dense computational power. That effectively traps them inside data centers, as they are far too heavy to deploy locally on edge devices like phones or commercial laptops. To run high-fidelity Inpainting on local hardware, the Moebius framework takes a different path, bridging the scale gap by designing a highly optimized task-specific specialist. The efficiency gap is stark. Flux.1 demands nearly 12 billion parameters and requires over 160 seconds for a full inference run. Moebius achieves its results with 226 million parameters, completing the same task in just 14 seconds. Brute force scaling has hit a ceiling for practical deployment. Moving forward requires a direct reassessment of how diffusion networks are structured for specific tasks. Engineers often struggle with the impossible triangle of architectural design, the attempt to simultaneously achieve low parameter counts, fast inference speeds, and high-fidelity generation quality. Historically, these goals have been at odds. Compressing a model to increase speed almost always results in a significant drop in the semantic coherence of the final image. Moebius breaks this pattern through a synergy of extreme architectural restructuring and latent space knowledge distillation. Look at the detail in the coastal village. The geometry of the red roofs is precise, and the waterline remains crisp and continuous, evidence that this lightweight framework maintains the complex structural generation typical of much heavier models. Raw speed and parameter reduction are irrelevant if the underlying semantic reasoning of the network collapses. The most obvious approach to structural compression is to swap out the heavy convolutions inside a standard diffusion unit for off-the-shelf lightweight operators. This typically involves using efficient mechanisms like depthwise convolutions and gated linear attention, or GLA. It is tempting to assume that simply dropping these operators into the network will save space without consequences. This graph tracks the Frechet inception distance, a metric where a lower score means higher quality. When these naive operators are swapped in, the error rate spikes from 32 to over 43. That spike represents a total breakdown in both spatial texture alignment and basic semantic reasoning. These lightweight operators simply lack the representational capacity required to manage the strict structural demands of image Inpainting. Gated linear attention is a clear example of the problem. While it processes self-attention efficiently, it mathematically cannot compute cross-attention. Without cross-attention, the network is entirely cut off from integrating external semantic global priors. Naive structural reduction triggers a terminal representation bottleneck, destroying the model's core reasoning capabilities. To bypass the memory constraints of quadratic attention, Moebius summarizes spatial and semantic contexts into fixed-size linear matrices, denoted as lambda. The local lambda module handles this by projecting latent features into multi-query keys and values, aggregating local semantics while maintaining linear complexity. The interactive lambda module solves the cross-attention limitation of GLA by utilizing lightweight positional embeddings. These embeddings explicitly inject spatial layouts into the external global priors, ensuring the model maintains a sense of geography. These lambda modules are combined with highly compressed depthwise convolutions and specialized mix FFNs. This final architectural assembly is the local lambda mix interaction block, or L-lambda-MI. The L-lambda-MI block successfully sheds hundreds of millions of parameters while preserving the crucial latent interactions and global priors that naive compression destroyed. There is an inherent hurdle. Extreme structural compression strictly limits the absolute representational ceiling of any network. Standard prediction loss on its own is not enough to recover that lost capacity. The solution is an optimization strategy called adaptive multigranularity knowledge distillation. To maintain training efficiency, this strategy operates entirely within the latent space, avoiding the massive computational cost of decoding back into pixels. The process begins with coarse grain distillation. This phase enforces an element-wise L2 alignment at the midlift's bottleneck, matching the lightweight student against the teacher at a 16 by 16 resolution. The second phase applies fine-grained distillation at a 64 by 64 resolution. This aligns the final latent predictions of the student with the high-capacity teacher. The framework then introduces a perceptual distillation constraint using the E-latent LP-IPS metric. Optimizing these different objectives simultaneously creates significant gradient instability. To maintain stability, the framework employs an adaptive gradient-based balancing mechanism inspired by GAN loss dynamics. This mechanism dynamically adjusts the loss weights based on the gradient norms of the model's key parameter sets. Balancing multiple gradient-based losses strictly in the latent domain compensates for the structural compression, enabling the architecture to reach its full representational capacity. These activation maps provide the proof. When we compare the 862 million parameter teacher against the 226 million parameter Moebius student, the representational structures are near identical across all spatial granularities. This parity translated into user preference. Moebius matched its teacher at 32%, while Flux 0.1 and Stable Diffusion 3.5 trailed at 23 and 12%. The network evaluates the globing context to flawlessly reconstruct the missing background, where competitors typically leave behind color inconsistencies and blurred artifacts. Moebius achieves 10 billion level visual fidelity while delivering a 15 times inference acceleration and shedding 98% of the expected parameter weight. For demanding computer vision applications, architecturally optimized latent distilled specialists provide an overwhelmingly superior performance to latency trade-off compared to the brute force of massive foundational models.